In this module, we will see how expectation maximization algorithm can be applied under MC setup, Markov chain Monte Carlo setup, the MCEM algorithm, how it can be implemented in R. Sometimes the several functions are available that can be used, or sometimes you may have to develop your own code to implement the EM under MCMC. And then finally, I'll show you one function called metrop, that how that metrop function from MCMC package can be used to implement EM algorithm for some specific data. Then MCEM algorithm would be applied on a simulated data set, and then that will end with the Metropolis algorithm. This Metropolis algorithm, and I'll tell the different steps of Metropolis algorithm, and with a small homework for you. In this module, we will see how EM can be implemented under MCMC setup. A difficulty with implementation of EM algorithm is that each step requires the computation of expected log likelihood. Besides the standard cases where the function q is available in closed form, since q is naturally expressed as an expectation, it can be approximated using Monte Carlo method. For z1.zt follows k, a distribution k, z given x, theta hat m, maximize a q hat theta given theta naught comma x equals to 1 by t, I equals to 1 to t log conditional likelihood theta given x zi. A more stable version relies on important sampling in order to avoid simulating a new sample for each new value theta hat m. Because the argmax, the maximized of likelihood over theta, can be expressed in argmax over theta gx given theta by gx given theta naught. That is actually the argmax expectation of theta over fx z given theta and fx z given theta naught given x. The approximation to log likelihood is then log L theta x is approximately 1 by t, I equals to 1 to n LC theta x zi by LC theta naught x zi. The stability of the above expression depends on the choice of theta naught in order to ensure a finite variance for this approximation. Let's use one example, the implementation of Monte Carlo EM on a simulated data. So let's first we'll implement the Monte Carlo EM on a simulated data. So this is an example of using MCMC package in R. The problem comes from a take-home questions on a PhD qualifying exam. The simulated data for the problem are in dataset logic. There are 5 variables in the dataset, the response y and 4 predictors x1, x2 or x4. A frequentist analysis for the problem is done by following R statement. You call the library MCMC and then the data logit you call, and then it's a logit model. So feed the logistic model as GLM, y left side of the formula is y and right side should be x1 plus x2 plus x3 plus x4. Data equals to logit, family is binomial and x is true. So it will generate the it will feed the logistic model and give you the results. If you generate the summary of out, it will give you the results of the logistic regression model. So here if you can see, this is the estimates, standard error and the p-value, and other AIC is available here, other the Fisher scoring iteration, number of iteration, that is 6, and many other informations are here. But this problem isn't about that frequentist analysis. We want a Bayesian analysis. For our Bayesian analysis, we assume that the same data model as the frequentist and we assume the prior distribution of 5 parameters, marks them independent and identically normally distributed with mean 0 and standard deviation 2. The log unnormalized posterior density for this model is calculated by the following R function. So this is let's suppose x equals to out $x and y equals to out $y, and the log unnormalized posterior function can be defined by this function, say LU post function. We are passing beta, x and y are the argument, and this is the returning, it will return the log unnormalized posterior function. Some computational tips in this regard, in the logistic model, the probability of y equals to 1 given x beta is actually e to the power eta divided by 1 minus e to the power eta. That is the probability of success, and eta equals to x prime beta. P can also be written as in this form, 1 by e to the power minus eta, and p equals to 1 by p, that is e to the power minus eta divided by 1 plus e to the power minus eta. Taking log, we get log p equals to n minus log 1 plus eta, 1 plus e to the power eta equals to minus log 1 plus e to the power minus eta. So that means we are just converting e to the power eta to e to the power minus eta. To avoid overflow, we can choose the case where the argument of e to the power is negative. We also can avoid the catastrophic cancellation when modulus of n is very large. If eta is very large, and if eta is large and positive, then p is equivalent to 1, q is equivalent to 0. So log p is then can be approximated by e to the power minus eta, and log q is can be approximated by minus eta minus e to the power minus eta. Similarly, the R function log 1 px computes log 1 plus x accurately also for modulus of x far less than 1. And exp m1 function compute the exp minus 1 accurately, e to the power x minus 1 accurately also for modulus of x less than far less than 1. So MCEM by Metrop function from MCMC package, the function is for MCMC for continuous random vector using a Metropolis algorithm. The argument to the Metrop function used here are an R function that evaluate the log unnormalized density of desired stationary distribution of Markov chain, an initial state of Markov chain, a number of batches for Markov chain. This combines with batch length and spacing to determine the number of iteration done. Additional arguments supplied to provided functions, and there is no burn-in arguments, although burn-in is easily accomplished in if desired. Here suppose first I set the seed as 42 to get the same results repeated times, and then the beta dot initial value, assign the beta initial value from the previous out object just to get a guess for beta initial, and then out equals to Metrop, then unnormalized log posterior beta initial, 1000 number of sampling required, say 1000, then x equals to x and y equals to y. That will give these are the object that it will return. And if you see, the returning objects are the accept is the fraction of Metropolis proposal accepted. Batch is n batch by p matrix. The batch means where p is the dimension of the results of out fun if out fun is a function, otherwise the dimension of state if that makes sense, and the dimension of state when out fun is missing. Initial, actually it return the value of argument initial, the initial value that we have assigned. The final object return the final state of Markov chain, the initial dot seed value of random seed, and the final seed, what is the final seed at the time of convergence, the running time of the Markov chain. Then LUD is the function used to calculate the log unnormalized density, either object or object dollar LUD from previous run. Then in batch is the argument in batch for object dollar in batch, and blen is the argument blen or object dollar blen. NS spec is NSPAC is actually the argument for NSPAC or object dollar NSPAC, and outfung is the argument or out function or object dollar outfung. How to control acceptance rate? It is generally accepted that an acceptance rate of about 20% is right, though this magic number is considered as a rule of thumb. So the argument scale of Metrop controls the size of the metropolis normal random walk proposal. The default scale is 1. Big steps give a lower acceptance rates, smaller steps give higher. It is also possible to make a scale a vector or a matrix. See help of the Metrop functions, the documentations that are there in the help might help you to understand get better understanding of the complete use of Metrop. So we are using one example here. Suppose the scale, I am using scale equals to sequence 0 to 1, length of out is 100. Just wanted to see how the acceptance rate varies over the choice of scale. And the acceptance rate equals to say array not available length of scale, and then for using a for loop for I equals to 1 to the total number of scale that scale values I assign, and then out equals to run the Metrop function again and for different scale values and get the acceptance rate. So there is a acceptance rate is a array that has the all acceptance rates for 100 different choices of scale value, and now the acceptance rate has been plotted against the scale value. If this curve is showing how the acceptance rate decreases with the increases of scale. This is a statement that has been given earlier, that the big steps gives a lower acceptance rate and small steps gives higher acceptance rates, that can be verified through this plot itself. The diagnostic for MCEM, the Metrop functions are, we'll start with a very simple time series plot. So let first get the object of Metrop, so out equals to Metrop out, scale equals to 0.42, and in batch is 10,000 say, and here acceptance is 0.21. It's okay, fairly okay. And then we'll plot the out dollar symbol batch, the batch that particular object stored all the sampling data for all the parameters for this particular model. So if you just pass through plot TS of out dollar batch, it will give you a time series plot of all 5 parameters samples that was generated. And to see the dependency of the samples, because you can do a ACF plot, autocorrelation function plot, just simple pass the out dollar batch through the ACF function, and that will generate a matrix plot of all different lags and the ACF functions, how it varies. The MC estimates and standard error. The out is for MC estimates and standard error. You just run out again, meter of out n batch equals to 100 say, and the function out func we define as a new function z, that cz and z square. It will give you the z and z square, and if you pass something, so out acceptance rate is 0.24 is acceptable. An argument out func that gives the functional of the state we want to average has been added with in metro. For this problem, we are interested in both posterior mean and variance mean is easy. Posterior mean and variance. The mean is easy, just average the variables in equation, but variance is a little tricky. We need to use the identity is variance of x equals to expectation of x square minus expectation of x. Hence, our out func return cz square from an arguments z. So if you just run this, and let's say foo equals to apply out batch to mean, that means column wise calculating the mean, that will give you the mean of mean, that is the estimate of all the parameters is mean. Now sigma square can be estimated as foo 6 to 10 minus mu square. Actually, that to get that expression, variance expectation of x square minus e square of x, so the mu square is corresponding to the e square of mu, and expectation of x square is actually the up to fifth is the parameter value, and fifth onwards it is the square of that. So definitely by these columns you can easily calculate the variance of the parameters. The Monte Carlo standard error are calculated from the batch means. This is simplest for means. For example, say apply again out dollar batch first 5 column 2 and just calculate the standard deviation divided by SQRT the out dot n batch. The square, that is square root of n actually. So square root of n, this component is the square root of n. That will give you the Monte Carlo standard error, and this is the Monte Carlo standard error. The extra factor square root of out dollar in batch arise because the batch means have variance sigma square by b, where b is the batch length as I mentioned, which is out dollar b length, whereas the overall mean mu have variance sigma square by n, where n is the total number of iterations, which is out dollar b length into out dollar in batch. To get the MC standard error for the posterior variance, we apply the delta method. Delta method is something like this. Let ui denote the sequence of batch means of the first kind z for one parameter, and u bar is the grand mean. Similarly, let vi denote the sequence of batch mean of the second kind z square for the same parameter of v bar is the grand mean. Then the variance is estimated by this expression. Variance is estimated by this expression. This implement here in R, say foo equals to apply dot this let's implement here, say u equals to say u dollar batch 1 to 5 and v equals to u dollar batch 6 to 10. 6 to 10th column and 1 to 5th column. Then u bar, you can apply u for column mean, v bar is the column mean of v, and delta tau is a sweep function you can use u to u bar. So second, column wise, you can use the u bar, and then delta tau is sweep v to u v bar. Then foo equals to sweep delta u to u bar to asterisk sign, that multiply that with the delta tau, and just by this expression you will get sigma square MCSE. So sigma square MCSE can be calculated by this expression. The foo equals to apply out dollar batch to this Now Metropolis algorithm, the jump function. Before we go to the Metropolis algorithm, use this jump function for get the hope you know what is jump function, but nevertheless I'm trying to give a primary concept of the Metropolis algorithm here. For Metropolis, jump function z must be a symmetric, that is j theta star given theta c should be j theta c given theta star, and most common jump function is taken as normal distribution. User must set the variance of the jump is by trial and error method. Turn to get a acceptance rate 30 to 70. Lower acceptance rate decrease the variance, and higher acceptance rate increase the variance. We can implement that Metropolis this in R, and start from to implement that in R. The algorithm is the start from some initial parameter theta c and evaluate the unnormalized posterior probability of theta c, and propose a new random parameter of theta star drawn from the jump function j theta. Evaluate the new unnormalized posterior p theta star. Decide whether or not to accept the new value. Accept new value with probability a equals to p theta star given p theta c, and repeat 3 to 5 third to fifth step till the required sample comes. So this is the algorithm for Metropolis sampling method. So I just giving this as a homework for you. You can implement that in any example in R. And the next module we will see how to implement the Metropolis Hastings algorithm in R. So I'm stopping here for this module. We have learned MCEM implementation in R and the use of metro functions for implementing MCEM, and then how to use metro function for Bayesian analysis, and finally ends with Metropolis algorithm and the different steps of Metropolis algorithm in R.